Now, let's go over an example that's a little bit more detailed than the one we did before to illustrate how rotate with left child works. So this function, first of all, is symmetric with rotate with right child, okay? And these are the ones that, these two functions are the ones that do all of the work. In the case of a single rotation, this function is invoked once. And in the case of a double rotation, it is invoked twice. So let's consider the binary search tree that we have depicted here. And let's calculate our balance factors. Okay, and I'm going to, so we've got a 0 here and a 0. And we've got 0, 0 here, and here, and here, and here, and here. This is a 1, 1 case. This is a 1, 1 case. And this is a 1, 1 case. And this is a 2, 2 case. And this is a 3, 2 case. Okay, and so as we look at this AVL tree, it is in balance, and we're now going to insert node 6 into this tree. And so 6 ends up being down here. Now let's recalculate our balance factors. It's 0, 0 there, and it and now this has height 1, and this is height 2. Okay, nothing has changed here, nothing's changed here. This is height 3. And lo and behold, it's way up here before we get an imbalance. This is height 4. So unlike the simpler examples I showed you before, the imbalance does not immediately happen at the point of insertion or deletion. And as such, the recursive, the unwinding of the recursion will cause us to have to rebalance every node. So let's take a look at this. We've got the root here being out of balance. Its height is 1, 2, 3, 4 on the left tree, whereas on the right tree, its height is simply 1, 2, or 1, 2. Okay, so the out of balance node is in fact the root. So let's circle that as our out of balance node. And so how did this imbalance come about? Well, from the perspective of the root, this imbalance came about by inserting a node, which we inserted. Remember, this is the guy we inserted, 6. We inserted a node into the left child of the out of balance node's left child. So even though down here, if I was to take a look at this, I might be inclined to say that this is an inner case. This is an outer case because we're talking about these two subtrees. And so the insertion happened in the subtree rooted at 12, which happens to be 35's left child, and 35 is 57's left child, and 57 is the node out of balance. Now let's back up for a second and let's take a look at the algorithm again, the balance algorithm. Okay, so here's the balance function. Okay, and we've determined that the left tree was the heavy tree. Okay, so that puts us inside this if. And now we want to find out whether the problem emanated from the left tree's left subtree or from its right subtree. And we notice that it came from the left subtree, so that a single rotation is warranted. And that is calling rotate with left child and passing it t, which is the parameter that came into the function. So that is in this case the node that's out of balance, 57. Okay, so in this particular function, so we're going to execute this function, rotate with left child. That's what was called from the previous slide. And so K2, it's important to notice that K2 is right here. Okay, that is the root of this particular subtree, and it was called from the previous function. And then we're going to declare a pointer K1, and we're going to make it point to K2's left. So K1 here is going to point to K2's left, which is node 35. We're then going to take K2's left. Okay, so we've executed this statement. We've taken note of that one. So we're now going to execute this statement. We're going to take K2's left and make it point to K1's right. Well, this is K2. This is K2's left pointer. We are now going to break this link, because we're going to take K2's left and make it point to K1's right. So we're going to make this connection right here. So K2's left now points to K1's right. Okay, and so we've executed this statement. We're now going to make K1's right, okay, which right now is pointing to 44 also. We're going to make K1's right point to K2. So we get this, and now K1's right is no longer here. Okay, and we've executed this statement. And at this point, for all practical purposes, the algorithm is nearly over, because we're just setting the heights here. Okay, we're updating the heights. But then the key thing that we do is we set K2, which is a reference to a pointer in this case. We set K2 equal to K1. So we break this and we make K2 point here to K1. Okay, so if we were to redraw this tree, I'm going to redraw it up here in the upper left. Remember, K2 is the root of the tree. Well, it is now 35, because that's K2 is pointing to the root of the tree. So if I misspoke, K2 came in as the root. It is now pointing to 35. Okay, and what's 35's right? Well, 35's right is this pointer here. So that's 57. Okay, and then what's 57's left? Well, that's 44. That didn't change at all. What's 57's right? That's 84. Okay, and here we have 61 and 95. Okay, and then 44 has 49 and 39. Okay, now what is K1's left? Well, that's 12, right? This is I'm sorry, K2's left. So what is now K1's left? Well, this is K1 here, and this is K1's left, so it's the 12. Okay, what's the 12's left? Well, that's the 4. What's the 12's right? That's the 28. And what is the 6? What is 4's left? That's null. 4's right is... Let's work out our balances. 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. This is a 1, 1 case. This is a 1, 1 case. And this is a 2, 2 case. And this is a 0, 1 case. And this is a 2, 1 case. And then this is a 1, 2, 3 case on the left. And a 1, 2, 3 case on the right. As we look at this, nothing is outside of the allowed tolerance of 1. There are no differences greater than 1. And we have restored balance to this particular tree following the algorithm. Okay, so the more complex part here is that we had to follow the algorithm very literally in order to be able to distribute the nodes here appropriately in the final tree. Okay, so let's recap as we've taken a look at binary search trees and a special case of binary search trees called AVL trees, which are self-balancing, and inserting the above sequence of numbers into the tree. If we just used a regular binary search tree without balancing, the tree would look like this. And so you see that it's a pretty tall tree. And as I previously mentioned, this is almost linear time. And in order to find, for instance, node number 13, I have to make 1, 2, 3, 4, 5, 6, 7 comparisons. This is a tree of height 7. And so it would take 7 comparisons before I could find value 13. And there are only 9 nodes in this particular tree. And so we're almost at linear time when we search this tree. Now let's look at an AVL tree. So using the AVL algorithm and inserting that same sequence of numbers into the tree yielded a tree of height 4. This means I would have to make no more than 4 comparisons that which would include both an equal, is equal to, and less than or greater than. But the maximum number of comparison levels here is 4, and I would actually find the value 13 after comparing it level 1, 2, and 3. So you can see that the AVL algorithm helps us retain the binary search tree structure that makes it easier to search, i.e. faster to search for values in a binary search tree. So let's do a brief recap. we've seen that binary search trees can degenerate from either the initial order of insertion or from later insertions and deletions, yielding something like the tree on the left. And we've also seen that once a tree becomes degenerate, it no longer yields log n search. And so we have to go to something that could approach linear time, i.e. order n. And finally, we've seen that self-balancing trees such as red-black trees or AVL trees will keep the tree more balanced. Notice that it is not perfectly balanced, but it is more balanced, and that improves the search. So that's basically binary search trees and AVL trees in a nutshell.